Okay, so yeah, thank you for all for joining in. Today we'll be discussing about particle swarm optimization. For a brief introduction of myself, I work for a wind turbine manufacturing organization as a structural engineer, and I am associated with Cellstrat as an AI intern slash researcher. So anyway, let's get started with this topic. Now, before we deep dive into the actual topic, I would like to glance through quickly on what is optimization and how optimization is actually used in machine learning. So, as all of you are aware, optimization is a very generic term that is used in a lot of fields like engineering domains to solve various problems in various engineering domains, in economics, etc. So, yeah. So, so the definition of optimization algorithm is something like this. So what you need to remember is that any job of an optimization algorithm or a job of any optimization algorithm would simply be to pick a solution or a best solution from a group of solutions. So let's say I have a set of solutions for a given problem, uh, and the job of the optimization algorithm would be to just pick the best out of it and give it to you. So having said that, we need to understand how or where optimization is actually used in machine learning. So to explain this, I've taken a simple example of a linear regression problem. So here you can see that there is area of flat on my x-axis and the price on my y-axis. So naturally, as the area of the flat increases, the price shoots up. So here what I want to do is I want to fit a line through this data so that if I want to predict what would be the price of the flat if my the area of the flat is around 3500 or so on. Yeah. So what I'll do is I will feed this data to a linear regression model. And what the linear regression model would probably do is, or would actually do is, fit a lot of lines uh, for the given data over a set of iterations. So let us assume in the first iteration, the linear regression model passes a line, a horizontal line passing through the centroid of x and y. Then it actually projects these y values onto the line which is drawn, and so this is the actual y, what is in green, and this is y predicted, right? So it's going to do this for all the data points, and once it does this, it tries to, the next step is to calculate the error. So the error is nothing but the distance between the actual and the predicted. So the most common error function, what is used to which is used to calculate the error for these kind of problem is called as the mean square error, which is shown here. So mean square error is basically it's a very simple formula. You're going to uh, find the difference between the actual and the predicted, square it up, and sum it for all the data points, and then you divide it by the number of data points. So after finding this mean square error, so let us plot it onto a graph where you have mean square error versus number of iteration. So in the first iteration, let's say we got a mean square error somewhere here. Then let's, after plotting this, the system goes to the second iteration where it slightly rotates this line, and you get and performs the mean square calculation and plots the mean square error again for the second iteration. So this goes on for quite a few iterations, and you can see that gradually the mean square error is decreasing as the line is getting better fit over iterations. Again, after some time, you would see that again the mean square error is increasing because it's moving away from the data points. Yeah. So from this graph, you can clearly make out that the line which represents this error would be the best fit for this data because the error is the least for this particular line. Okay. So how does the learning or the linear model finds this which is the best fit line is actually very simple. So if I just draw this a line passing through these data points, and then you get a convex shape like this, then what the learning model does is actually it tries to find the slope at each and every point. Yeah, like this. So at this particular point, since the slope is horizontal, or you can say there's no slope at all, this value or the gradient would tend to zero, and then the system would say that, okay, since the gradient is approaching to zero, this would be the best solution available. So the most common algorithm which is deployed to find the optimum solution using this principle of gradient is called as the gradient descent algorithm. So is there any questions till now? Okay, I don't see any questions. So moving forward. Okay, so even though gradient descent algorithm is the most common and popular algorithm, it comes with its fair share of problems. So it has few disadvantages. So first one being that it cannot be applied to non-differentiable functions. So let's say that in future some of you would go on to find a new cost function, not like the mean square error, some other cost function like this, where it is a discontinuous function and it's not differentiable at certain points. So in these cases, you won't be able to apply gradient descent because the system will not be able to find the slope at these points. So this is one of the major drawbacks of your of the gradient descent or any optimization algorithm that works on the principle of gradients. So if you have to use a gradient descent for your optimization problem, then it is mandatory that your cost function or error function is differentiable at all points. So that could be a drawback. Another problem is it cannot be reliably applied to non-convex problems. So as I was showing in the previous slide, the mean square error versus number of iterations, the graph, we saw that we got a beautiful convex shape. Okay, now the mean square error gives this beautiful convex shape, and we know that the minima is only one. You have one global minima, but not all cost functions would give you this beautiful convex shape. So you might get some irregular shapes like this for various other cost functions. So what is the problem with these shape? So if I draw this, something like this, yeah. So here, what happens is that the model or the optimization algorithm gets stuck at these points, which is called as the local minima. So even here, when it starts to draw the gradients, even here the slope would somewhere tends to zero, but this is not your optimum solution because the error is least somewhere at this point, right? So it gets stuck in something known as local minima and would not reach the global minima. So the way another analogy to look at optimization problems would be to imagine it to be a landscape exploration problem. So let us imagine that we have a particular landscape filled with troughs and valleys, or let's say plateaus and valleys, and you have been sent on an adventure to explore the deepest point of this landscape, and you're also given a measuring device to find the depth of this landscape. So what you would do is you would slowly make this progress. You would go here, and even then you start to go up, and you would think that the depth of this landscape is increasing. So you might stop your adventure somewhere here or here, imagining that you would have found the lowest point of this landscape, and you will not further expand your exploration. Another problem could be that even if you manage to evade all this and go through the deepest point, it might take a lot of time, right? It may take a lot of time to reach this deepest point of your landscape, which is the global minima. So this is one of the biggest challenges in gradient descent, getting stuck in local minima and taking a lot of time to reach the global minima. And another one of the major drawbacks is that it requires hyperparameter tuning, like the learning rate. So I think most of you are aware of what happens when you increase or decrease the learning rate. So basically, if you give a very high learning rate, the solution might never converge. And when you give a low learning rate, it might take a lot of time for the solution to converge to a global minimum. Uh, do you have any questions till now? I'm just going to pause here for a second.
Yeah, I don't see any questions so far. I think it's all good.
Okay, fine. So moving forward, uh, to overcome these problems of gradient descent or any optimization algorithm that works on the principle of gradient, we need to start looking out for other options. So to help us, we have other optimization algorithms like the particle swarm optimization. So what exactly is particle swarm optimization? It is a meta heuristic optimization technique. So what do you mean by meta heuristic? So we can divide this meta heuristic into two terms, let's say meta and heuristic. So heuristic is nothing but finding a solution by trial and error method, and basically heuristic techniques are cater to only one type of problem. Yeah. So it is a must to be aware of what problem you're solving for heuristic problems, whereas meta means advanced search approach, where it can be generalized to any problem. So you really don't need to be aware of what actual problem you're solving. So it can be generalized to a set of problems. So you can just say meta heuristic is nothing but advanced search by trial and error, to put it in very simple terms. Okay, so another thing is it belongs to family of swarm intelligence. So what exactly swarm intelligence is that? Swarm intelligence refers to collective intelligence, which you can observe in social animals like bees, ants, birds, etc., where they interact with each other to solve a common problem. So under swarm intelligence, you have a lot of algorithms, a lot of optimization algorithms like the genetic algorithms, the ant colony optimization algorithm, the PSO itself, and ABC refers to artificial bee colony. GSO refers to glowworm swarm optimization, and then you have the cuckoo search algorithm. So today we will be taking only the PSO. We'll be discussing a lot about PSO. So PSO in particular is inspired by the behavior of bird flocking or fish schooling. So when a birds flock, or so let's say fly in a group, it's called as flocking, and fish swimming in a group is called as schooling. So this PSO is inspired by the behavior of these birds flocking and fish schooling. And another advantage, or you can say a feature of PSO, is that it can search very large spaces of candidate solution. So it simply means that let's say you have a lot of solutions in a group of solutions, very large number of solutions. It can easily search the best solution out of it. Okay, and the best of the property it has is it does not use the gradient. So a lot of the problems which you saw in the previous slide can be eliminated just because it does not use a gradient, and the cost function need not be differentiable. So this is one of the major advantage which you find with PSO or any of these algorithms what I've shown here. Is this clear, or you have any questions?
Yeah, I guess keep going. So if they'll ask if they have any. Audience, feel free to
Okay,
ask any questions all throughout.
okay. So let me just pause here. So this is an ant colony which is trying to get their food to the nest. So as you can see that they are moving in a wrong direction, right? But their nest is somewhere in this particular direction. So what happens is that if you observe, the leader comes in and redirects the team towards the nest. So there is some sort of information being shared as a group, and they are trying to solve a problem as a group. So this is one of the example of swarm intelligence. So they did this research on a bunch of ants, and here you can see that they have tricked the ant to lift an object which is much heavier, but as a group they are able to solve that problem with ease. So what we can observe from here is the collective effort is always better than an individual effort. And these kind of the problem solving capabilities are always seen uh, in any of these social animals. So the next example what we have is even better. It's called as the waggle dance of bees. So the bees when they have to find food, okay, so sometimes they encounter food scarcity. So each individual have to go find a, a patch of food, and they have to come back and report it to their group as to where the actual food is. And the way these bees communicate this is quite amazing. So they do, in order to communicate where the food is, they actually do something known as the waggle dance. So let me just take you through that. Yeah. So basically this is the bee which has gone and found out where the food is. Now it is trying to communicate this to uh, the bee colony. So you can see that this particular bee is first trying to catch the attention of the other group of bees. Yeah, and then it's trying to make few circular motions and trying to vibrate. So these it's very intense that or very intricate motions that it makes. So longer this motion, it means that the path or the distance to the food is quite like it's far away. Shorter this circle means that the food is close by. So and apart from communicating the distance, it also communicates the direction of the food, and it's quite amazing that how they find the distance find the direction. So yeah, so here actually this particular line with respect to the sun and the angle gives the direction to the bees on where to go and find the food. So again, this is an example of collective intelligence which is coming into play, and where a group of individuals are coming to solve a common problem. Okay, so moving forward, we have what is known as the Starling murmuration. So our PSO, particle swarm optimization, is mainly based on this flocking of birds, and in that what the flocking of the starling is known as the murmuration. The reason why they do is to avoid predators and again find food. So the way they move in group is also quite fascinating. So you can see them making these shapes and the hundreds of starlings going in a group without colliding with each other with each other. So how they do is actually very simple. So let's assume there is a starling here and it's surrounded by four other starlings. The movement of this particular starling bird would be dependent on individual movements of these four starling birds. So in that way, they know how to move as a group without colliding with each other. Okay, so these were the few examples where you could observe swarm intelligence. Now moving forward. Okay, now we will get into the working mechanism of PSO. So how exactly PSO works. So before we get on to the actual math, let us understand PSO on a very intuitive level. So let's assume that let's go back to the landscape problem, right? So let's assume you have some landscape like this, okay, and you are asked to explore the landscape to find the depth, the deepest point in the landscape. So the only difference here with respect to gradient descent that is that you will not be alone. So you will be accompanied by say a few of your friends. Okay, so and all of you will not be starting at the same point. So you will be scattered at different points. Let's say you were airdropped into this landscape at different points. Now you will be having a a measuring device as well as a communication device. So uh, all of these individuals start making their movements. Let's say you come here and this individual comes here and he measures movement or depth here, and this particular individual, when he reaches here, he reports depth. Okay, so now you can see that the depth of this depth measured by this particular individual is lower compared to these two individuals. So it communicates this information to them and they start to move in that particular direction. Similarly, this also tries to move in that particular direction until he reaches here. So when he reaches here, okay, uh, he will communicate this information to other individuals, and they have, since this is the deepest point compared to this, they will again change their direction and move towards this particular direction. So you can see that in this way you can explore the deepest point much faster because you are accompanied by friends of yours, and since there is a lot of communication going on, you will be certain that that is not the actual deepest point what is explored by a particular individual. So this is known as the global best. Okay, let's say G best. And the movement made by these individuals, and if they find out something slightly deeper compared to their previous positions, that would be your personal best or individual best. So is this analogy, did you get this analogy or you have any questions?
So, Nikhil, you are saying here that the leadership keeps shifting. So, whichever
Yes,
particle is in a better situation, suddenly that person becomes the guiding light, and
yes, exactly.
others try to match that. Uh,
Yes,
But what about the physical characteristics of the individual? So some birds may be more mature or powerful, more insightful maybe, and don't they try to dominate? So there is no sense of domination. It's a perfectly democratic country.
Yeah, because I know, I think you are referring to the greedy approach where you, yeah, is that what you're referring to?
No, I'm
Where,
thinking that naturally some individuals will be more stronger physical traits or just natural leaders or and so isn't there any sense of domination by any individual? It is fully democratic that whoever is best position others start following that individual.
yeah, so apart from following the global best, they will also try have a memory of their personal best. Okay, so how it works is that if their personal best is, or if the global best is lesser than their personal best, only then they will move towards that direction. Else they will be searching in, with respect to their local area itself. So definitely there is no, yeah, it's kind of, it is democratic. You could say it is kind of democratic.
So there are some questions here. You can see them in questions maybe.
Okay, I'm not able to see the questions.
You can expand the questions tab. There is an expand button or pop out. There's a pop out button on the questions tab.
Okay. Okay, it asks how many directions are there for, how many dimensions are there for direction. So yeah, it solely depends on the problem you're solving. So in this case, let's say it's in a two-dimensional problem. Can you explain third point? Which third point are you referring to?
I
Sorry,
think
I
that
missed that.
was some time back, so that's okay. You can skip that. It was long back. So I think in a 3D space, when the birds are flying in the air, so it's a three-dimensional space,
Yeah,
and so that creates a 3D environment in space in air. And so the global best is basically we are saying that some out of let's say 1,000 birds, one bird seems to contain the point of global best, and then others try to move towards it and adjust their position, but then
yeah,
global best shifts to another bird, then
it
everybody else tries to shift towards the new global best.
exactly.
So
Yeah,
back and forth, the global best is a moving target itself, and at any step, all others try to move towards that bird which has the global best score. So there's some kind of scoring. Every bird has a score, and whoever has the global best score, sort of others try to go towards that one.
yeah.
There is some other question here. You can see. Can you see the other questions, Nikhil?
Yeah, so yeah, I can see that here the initialization seems to be matter a lot. Also the number of entities. Yeah, actually, I wouldn't say initialize. Yeah, to some degree, initialization does matter, but if you have a pretty good number of particles in the swarm, then if they are scattered, then it should not matter.
So eventually they will converge. It's just a factor of time, right? They could
Yes.
initialize at any stage, but eventually they'll converge. It's just
Yeah.
a number of iterations it will take to converge to the global, the
Yes.
final goal, which may be the food destination or whatever.
Yeah.
Uh, but in the starling murmuration, you were saying they were just going around in that region for a long time.
No, that
So it's
is
not like they were trying to move. Okay.
no, no. Yeah, no. That's just for a representative purpose. Actually, it's not actually. It is
No,
just
are we
there.
saying that the swarm of birds is actually trying to move to some location? Is that what is happening? What is the
Yeah.
eventual goal?
Okay, so in when you take with respect to this optimization, you are given a task to find the global minima, right? So let's say the food is where the global minima is, and the job of the swarm would be eventually to reach that location of the food.
Okay,
That is
so
the global minima.
eventually the flock has to reach there, so it sort of juggles among itself and goes in that direction. Okay.
Yep.
Uh, Next question is, how can this be used in networking of IoT? Uh,
I'm not sure with
yeah, I mean,
IoT.
we'll have to think about it. I mean, we have to find the concept of a swarm, right? Unless you can find a concept of flock or a swarm which is cooperating to achieve a goal, it will be hard. But I'm thinking something like a sports analytics. I'm just giving a thinking very wildly here. Maybe let's say football. It's a team of 11 players trying to score a goal, right? So there could be some kind of swarm intelligence applied. So just a sideline thought, like a football team trying to reach the opponent's goal post. Uh, what is the best way to get started on swarm optimization if one knows basic ML? What is the prerequisite? Nikhil?
uh, you can what is your end goal? Is that do you want to use that in your ML model? This is what your question is referring to. Then you can just know how the
See, I
working
think you just explained gradient descent. So knowing ML is definitely a prerequisite, I'm thinking, right?
Yeah,
So
but
the
also
point of
let us
global convergence to global loss.
yeah, that is true, but let us also not forget that optimization is also a very generic topic, and you need not necessarily apply it only to machine learning. You can just apply
Okay.
to any field. Yeah. So
So,
if you want to take
okay.
PSO and apply to any other engineering problems, you can do that as well.
So you
Okay.
don't have a prerequisite of knowing ML here, right?
Yeah. No. But this webinar is I've catered to the needs of ML. But if you want to implement PSO elsewhere, you don't need to know ML.
Right. Next question is, as they reach the global best, will they miss out on new best? See, the global best is a moving point. So in the current time step, this one bird is the global best location, but maybe in the next time step, another bird takes over the global best, mental, right? So the
Yeah.
global best keeps shifting.
Yes. So
And
I think we can
yeah,
explain this better in the coming slides where there are
yes.
few calculations that shows how it actually works. If that's fine.
Can there be a situation, which one question is there, how do we initialize? Can you face a situation where it does not converge because somehow your initialization was wrong or something? Can you miss convergence because you didn't start correctly?
Uh, yeah, if that would be rare, but it is possible that all of them would move to a local region. That all of the but it's very rare. I don't think it's possible because I'll tell you why. Because the initialization is done in a random manner. So what are the odds that all the particles would initialize at the same position? That's very rare.
Okay, there is one more question. Can we use it for support vector machine instead of convex optimization?
Yeah, you can.
Uh,
Actually, there are few papers which show how PSO can be used in supervised learning. There are papers already. I think you can refer one of them.
so you are saying instead of gradient descent algorithm, I can use swarm optimization to arrive at
Yeah,
global loss minimum. Okay, interesting.
yeah.
Okay, that's good to learn. At the end of optimization, will they ensure the whole area gets covered?
That depends on how many. Yeah, that depends on how many particles you're using. Like say, if you use just two particles, yeah, it can cover landscape, but it might take a lot of time.
Okay, I think there are no further questions. Maybe you can continue.
Okay, fine. So moving forward, so as I was telling the analogy of exploring the landscape. So you along with your friends would be known as particles, and each of you will have a property of velocity and position. Position is nothing but your current location, and velocity is something which you will be using to communicate with your fellow mates to direct them to which in which direction you need to move. So velocity is like a vector, so it will have a direction, and it will also say by how much you need to move. So so this is the equation to find the velocity or the direction in which you need to move and by how much. And the new position would be the current position plus this velocity. Here vi is the velocity of the ith particle, and pi is the position of the ith particle. P best is what I told, the individual best of each of the particles, and G best is your global best of the entire swarm. So here you can see R1 and R2 are random numbers which are between 0 and 1, and these three are your user input or hyperparameters. W is the inertia of a particle, and C1 and C2 are the acceleration coefficients. So we'll discuss about this in the coming slides, maybe with the help of an example. So if you don't get this equation now, that's completely fine, because we'll try to explain this with the help of an example.
No, I think it will be good to just throw some intuition here on the equations. Uh,
Yeah,
so in the position, which is the simpler equation, you are saying position at time step t plus 1 is equal to the previous position at time step t plus a certain velocity at t
yeah,
plus 1,
yes.
right?
So it's
And,
basically
yeah.
you are moving with the help of the velocity. So this is your previous position, and since you get a new velocity, you will be moving with that particular direction and by so much magnitude to get your new position.
And in the left equation, you have the new velocity for time step t plus 1, which is weighted product of w into the previous velocity in time step t. And then you
Yep.
have two expressions on the right where you are comparing the current particle's best position minus PIT, and then also the global best minus PIT. So you are applying relative addition of personal best versus previous position and also global best versus previous position,
Yeah,
right? So
exactly.
C2 R2 act like weight. C2 is a acceleration. So how much you accelerate from current position based on your personal best, and then from current position based on global best. So R1, R2 are weighting of some kind. So actually the equations are intuitive. They are not that difficult.
Yeah. So
Sorry to interrupt. Kindly continue. Yeah.
yeah, so I have a separate slide wherein we'll dissect this velocity equation and try to understand each of these terms. Okay, let's okay, this is the pseudocode of PSO. So it starts with first initializing position of the swarm for each particle and its velocity randomly. Then what it does is it finds for each of the particle, it finds the fitness function. So your fitness function is nothing but your error function or cost function, whatever you like to call it. So if the fitness value of the current fitness value is better than their personal best, the personal best gets updated, and that is done in one loop. And next, what it does is out of all of these uh, personal best, it tries to find the global best. Okay, and this goes on until a stopping criteria is satisfied. Okay, so I think you will understand better when we solve this particular problem. So here what we are trying to do is we are trying to minimize a sphere function using PSO. So this is how a sphere function is given, and here I'm using the sphere function within this particular domain. So so much, so I'm not worried about this. I'm restricting the landscape, and I'm using for 2 dimensions. That's why you have x1 square plus x2 square. So the first step would be to set the user inputs or hyperparameters. So here I'm setting the number of particles, the inertia, and the acceleration coefficients, and the number of iterations. Okay, so step 2 would be to initialize the random position for each particle. So you need to ensure that it is within the bounds, the landscape. So here I've taken 0 to 10. So you need to ensure that the position of the particle is within these bounds, and then we'll calculate the fitness value for these positions. So you have positions for 2 particles, that is P1 and P2, randomly initialized. And then if you see, you're calculating the fitness for each of the particles. So it was x1 square plus x2 square, so basically it's 3 square plus 2 square for this 13, and you have 2 square plus 1 square 5. Okay, then you what you do is you initialize the random velocities also as well for each particle within the bounds. So that's what I've done here. I've defined a class called particle, and then I'm doing some initialization of positions and velocities. Okay, now since we have initialized, we need to find the personal best for each particle and the global best. So here personal best would be the same as the particle position itself, because we have not, the particle has not yet started moving, right? So whatever best position would be is the current position itself, and the fitness function of that particular position is will also be the same. So which is the global best? So it's easy to know here, since 5 is the least of the fitness function between these two. So this will be your global best fitness value, and this will be the position 2 comma 1. Okay, so once this is done, we start our iteration. We generate the random values r1 and r2, which is required to calculate the velocity, and then we plug in these values into this equation. So here you can see 0.5 is the inertia value, and 1 3 is your velocity of the first particle. So we are doing this for the first particle, and then c1 would be equal to 1, c1 equal to c2, and then we are taking this random variable. So remember, this is for the number of random variables depends on the dimension. So this for x1 x2. So if you are having more than 2 dimensions, then you'll have another random number. Then you are multiplying this with p best minus uh, the current position. So here the p best and the current position is the same. So you basically nullify this part, just because this becomes equal to 0, and then we calculate the next portion, that is c2 into r2 into global best minus the current position. So this is the global best 2 comma 1, and this is our current position. So we get a new velocity. So and then we add this velocity to the initial position to get the new position. So we started off for particle 1, we started off with this position, and now after the after updating, the new position is 3.3 comma 3. So we repeat this step for second particle as well. So you need to do this for all the particles in your swarm, and so this is also carried out in a similar fashion, that you plug in these values and you get a new position for the second particle. So the previous one was 2 comma 1. Now we are ending up with 3 comma 3.5. So I've just defined that in a code here. So I've broken down this particular equation into 3 groups. Yeah, I call them as momentum, cognitive, and social. I'll discuss about this in the next slide. Okay, So now again, after this is done, for each of the particles, we need to again find out the p best and the global best. So this is your new p values, and if you see, compare these fitness functions. So the new fitness function is way higher than your previous fitness function. So naturally, the p best will not change. It will still remain the same 3, 2 and 2, 1. Okay, and the global best also will remain the same because uh, the p best is the previous p best is retained, and the same thing to go with f of g best. So nothing, that's nothing but fitness function of this g best. So this ends the iteration. So so one important thing to notice here is that when you start the second iteration, you're going to start with the new positions. So you won't be starting with the p best. So this might be slightly different than the genetic algorithms which you have seen previously, where there is a concept of uh, fit best fit comes into play, that they are incorporated into the population. But here, if the solution is bad or good, it doesn't matter. It will get incorporated into the population, and the iteration starts from this new position. So and new velocity. So again, the loop would go back to this generate random variables and generate a new velocity and calculate the new position. So this would go on until we reach the f of g best, which should be equal to 0 for this function, because the minima of the sphere function is at 0 comma 0. Sorry, fitness function is 0 and it's at 0 comma 0. So this operation would continue till your f of best becomes equal to 0 and g best will becomes equal to 0 comma 0. uh, is there any questions? Let me just look at questions.
So essentially, one particle has two characteristics. One is the position of the particle. The second is the velocity of the particle, right? And
Yes.
so each particle has two characteristics, and these two characteristics are repeatedly updated in every successive iteration. Now, the
Mm-hmm.
fitness score is that custom calculation based on your domain problem here, which is minimizing the curve function, right? Or
Yeah,
sphere
yeah.
function,
So
x1
fitness
square
function,
plus
yeah,
x2 square.
yes,
So
you
that's
can
your fitness score. So that is not particle centric, that's your system requirement, right? Or problem
exactly.
requirement, or the
Yes.
optimization problem. That fitness score is that x1 square plus x2 square. That is custom to this particular situation. But the
So
particle in all circumstances has two factors, which is velocity and a second is position. And both of those get adjusted as per that equation every iteration, right?
exactly. So you can refer, okay, you can relate fitness function as your cost function or error function. So your x1 square plus x2 square would generally mean it would be an error function like mean square error or something like that. Yeah,
But
and
in some cases, I could be trying to maximize it also, right? It
yeah,
need
yeah,
not
you can do
always
that
be
as well.
the,
Yeah, minima. Yes, it can be
yeah,
a maxima as well. So it would be safe to say to arrive at global optima.
right. There is a question here. Uh, will it be applied in medical image classification as optimization algorithm? Can you use such kind of logic for medical image classification?
Uh, I'm not sure in particular about medical, but there are a lot of papers which have referred to where they have used POS for training neural networks. So yeah, there is a chance, but
Hmm.
we have to look into it.
Okay, so there is a way to apply swarm intelligence to
Yeah.
neural network optimization. Yes. Uh, there is one more question. What is the level of maths required to understand swarm optimization? Is there
I
any
mean,
ready-made Python package we can use for this?
yeah, there is something called PySwarm which is available, but I have not dwelled into it. But yeah, they say it can be used for POS optimization. Yeah, there's something called PySwarm, if I'm not wrong. Yes.
What level of maths is required to understand this topic?
I mean, if you see, this is all the math. It's simple arithmetic calculations. That's it. You're just multiplying and adding, and finding out the new position. That's all the math is involved. There's nothing more.
Is that true of just PSO or in general swarm intelligence, Nikhil?
Uh, I that I have to look into, but if you have observed the genetic algorithm presented by Bhavesh, even there you could see it was the calculation was always limited to basic arithmetic.
Right, right. Could you please elaborate on how the direction is set in velocity?
So yeah, so if I say v1 is point 0.3 comma 1, so let's say so yeah, so let's say this is point 0.3 comma 1, and you are at this position, and this is the new position, so it will try to move in this particular direction.
See, I am also lost on the sense of direction. So I got
Hmm.
the point that a particle has position and velocity. But what
Hmm.
about direction? There is no directional intelligence in these equations.
Uh, yeah, as such, there is no directional intelligence because yeah, it can move in any direction to find the yeah reach at these positions.
Okay, so the position is a coordinate in that
Yeah.
space. So I
Yes.
guess if I get the position, I know where to go. So I got my direction through the position. Okay. So the position is also incorporating where I have to reach. The pt plus one gives a directive to that particle to move to that location pt. So pt plus so p is a coordinate in that 3D space. I guess that incorporates the direction. Position is the direction. Okay. No, I think we got the direction covered. Earlier I was confused, but now I'm thinking the position in that 3D space is a specific coordinate, right? So it that pt plus one tells me where I have to go from current position. So pt ends up into pt plus one. So direction got covered, or it's
Yeah.
embedded in the position part of it. So no other questions for now.
Okay. Can we move forward then?
Yeah, I think so. Yeah.
Yeah. Okay. Okay. So now let us break this down to you know three parts. This complete equation, and you will get a better idea of how this equation is working. So here we have this part known as momentum, and you have this part which is known as cognitive, and you have the last part which is known as social. So what this part is doing is basically it is memorizing the flight direction of the previous flight, that is vi of t, and it what it basically does, it prevents the particle from drastically change in direction. So so if you have a higher value of w, and then you say that yeah it would more tend to be closer to its past direction than the future direction. So, and it's also referred to as inertia, a sort of resistance to moving, a sort of resistance to the movement. Then you have this part which is called as cognitive. So here if you see, it is basically finding the uh, performance with respect to its relative performance. So here you are looking at individual best and then you're subtracting it with the current position. So it basically remembers individual memory of the position which was best for the particle, and it's also known as nostalgia of the particle. So, and here you have something called as a social, because you are taking into account of the global best. So this quantifies the performance of the particle relative to a group of particles. So each of the particle will, apart from being drawn towards its individual best, it also be drawn towards the group best. So let's say if I have a, say this is my current position, and this is my personal best here, and this is my global best somewhere here, okay, represented by this vector, then its next movement or direction would be a resultant of these two. So that is what this cognitive and social does. So it somehow controls the direction of the particle in the next iteration. Okay, now coming to this point. So what will happen if you play around this acceleration coefficient, which is a user parameter? So this C1 and C2 are indirectly attached to the uh, cognitive and social. So if both of this becomes equal to zero, they will move in the same direction until same direction as your previous direction until the bounds are met. So if you have a search space and in the initial step the particle is moving in this direction, it will just continue to move in this direction until uh, the search space boundaries are reached. And what happens when C2 is zero? So what if this part is zero? So then there is no swarm intelligence actually. So it will not have any information of the global best, and it will just keep rotating around its local position. And the other way, if this is best, if this C1 becomes equal to zero, then it will be moving towards, all of the particles would be moving towards one single point without taking into account of p best, because there are times when this p best would be better than global best, and that uh, direction will not be taken into account if this becomes equal to zero. So ideally you want this, where particle would be attracted by taking into account of both p best as well as g best. And if you have low values of C1 and C2, it's like you will have a smooth movement of particles. And if you have very high values of C1 and C2, you have a abrupt movement of particles. Like you can relate this to learning rate, I guess, if you have a very high learning rate and very low learning rate. Okay, yeah. So before we move on to the advantages, I would like to go to the code demo. Okay, in this we'll be optimizing a function known as the
Uh,
Rastrigan function.
can you increase the font a little bit in that code?
Yeah. Okay. Any idea how do I do it?
Try Control plus on your keyboard. Maybe that will do it. Windows Control plus. Yeah. I think this is increasing the font to 20. Yeah.
Okay.
I think this is okay.
So yeah. So here, if you see, you can see there are a lot of optimization test problems. So basically, we want to try out one of these problems where there are many local minimas. So I have used the Rastrigan function, where you can see it has a lot of local minimas, and its global minima would be at 0 for position x of 0 comma 0. and this is the equation for that cost function or fitness function. And it is a bond between these values. Usually it is tested for these bonds for 2 dimensions, that is minus 5.12 to plus 5.12. And here d would represent the number of dimensions. So if you have 2 dimensions x1 and x2, you will use d as 2. So similarly, you have a lot of functions which you guys can try out, the Achille function or the drop wave functions, which are fairly difficult to optimize. So if there are any new optimization algorithms coming up, they usually go through these standard tests of going through all these functions. And in today's problem, I've just taken the rastegram function. So here I'm just importing the uh, all the libraries, and I'm just plotting the rastegram function just for visualization. So
Now, these kind of functions, do they find usage in, let's say, mechanical design or industrial design? Uh,
hello,
yeah, do these kind of functions you are showing that list, are they related to mechanical or industrial design?
uh, Vivek, I'm not very sure on that, but what I'm
Okay.
clear is that uh, sorry.
No, no, that was the question. So, is this related to mechanical engineering or industrial optimization techniques or something? But maybe not. Okay.
Yeah, so it's not associated with anything in particular. So okay, so this is what the rastegram function looks like, and its minima is, as I told, it's at 0 at 0 comma 0. Okay, here I am defining the user parameter, that is the number of dimensions, the lower and upper bound, and number of particles, and the inertia value, acceleration coefficient, and the number of iterations. So here I'm defining class particle, and I'm giving its initializing the position of the particle and its velocity for each of the dimensions. So this is, I'm just again defining the function now with respect to the positions, because we'll be calculating the fitness with respect to the position. So here I've just used it as x1 x2 just for plotting this graph. Okay, this is the function to define the new or calculate the new velocity. And here what I'm doing is I'm creating a swarm in the range of x to the total number of particles, so that is 10 particles. So now what it will do is it'll create 10 particles, and it will initialize the position and velocities of all those 10 particles. Yeah, so here we are now finding uh, the global fitness and global positions. So as you know, before we start the iteration, this would be same as the initial fitness and initial positions. So this is where the actual loop starts. So here we are, for each particle in the swarm and for each of the dimension, we are calculating the particle velocity, and and then we are ensuring that the velocity is within the bounds, and then we are calculating the particle position with respect to this velocity which has been found out, also ensuring that the particle positions are within the bound. Then we are calculating the fitness value for the new particle position, and figuring out which is the uh, particle best and the global best. So let us run this loop. Yeah, so you can see that it has started with 3, and it needs to go to 0. And at some point, yeah, here you can see it's converging very fast at iteration 38, because this is almost equal to 0. So here I've not given a stopping function. So you can always give a stopping function with respect to the error, how much error you want, and then you can stop that loop and come out of the iteration. So you can see that global value is 0 at 0 comma 0. So we can try this out for another function. Let's say for this particular function.
Hey, Nikhil, quick question here.
Yeah.
You said number of particles too in your PowerPoint part.
Hmm.
Now, doesn't it need a large swarm? Can two individuals working in a swarm fulfill the objective?
No, that was just to show you the calculation. Yes, definitely you need more particles.
So, how do you decide what's the minimum number of particles you need to create a effective swarm?
That again depends. It's a hyperparameter. So
Okay,
it depends on your problem at hand. So this is the
okay,
function what we are going to optimize now, and here you can see that it has local minima and sorry global minima, and its global minima is at minus 2.9, somewhere around minus 2.9. So let's run this for the same thing. Oh, not sure. So yeah, so here you can see that it started at minus 2.69. So it nearly reached the global minima in the first iteration itself, and it nearly converged very quickly. So yeah, so that is the advantage of using POS. So PSO, sorry, it converges very fast to the local, sorry, global minima. So it's a very simple code as such, because I think anybody can, you guys can refactor this code and make it even better, because all you have is basic arithmetic calculations and few comparisons. Okay, so there any questions?
yeah, I'm thinking of a interesting use case of social networks, right? Because
Mm-hmm,
a social network has a group of people, let's say a population of a country trying to
mm-hmm,
do something, or even elections or some other. So wherever there is a crowd, there is a swarm, right? So, and wherever there is a crowd, you can build swarm intelligence, perhaps. But yeah, it's not clear to me yet how you will think of a swarm when you're trying to optimize a neural network, perhaps, because well, you could say in a neural network, let's say I'm given 1000 images for image classification. So there are
mm-hmm.
1000 images which could cooperate in a swarm, perhaps. I'm just guessing. Or any other data set which has, let's say, 1 million samples, and they could cooperate to achieve certain objective. So I'm just thinking how swarm will apply to machine learning and deep learning problems. So your view
Okay,
is that we can replace gradient descent or ADAM optimizer with swarm,
yeah,
algorithms, right?
yeah.
Okay. Because we do have a sense of a swarm when we do mini batch gradient descent, right? So there is a sense of a crowd operating together to achieve it, or incremental gradient descent. So we are looking
Mm-hmm.
at successive improvement of my my model by incremental or batch gradient descent. So there is already a concept of a community of samples working together. Maybe there is some overlap through some papers you mentioned.
Yes.
So it will need we have to look at how to apply to MLDL actually. Uh, Audience, any other questions? Very interesting new topic for our AI lab group. Any other questions? Now, does this come under artificial general intelligence or does it come under reinforcement learning typically, Nikhil?
You actually find its users in reinforcement learning. It does not come under reinforcement learning. It comes under, what do I call it? It is a type of optimization algorithm. So wherever you want optimization, you can use it there. So it's not specific to any one particular domain, I would say. That's how I put it.
Right, right. That makes sense. You can continue actually. You can
Yeah.
take questions in the end.
So now we are looking at advantages and disadvantages of PSO. So one thing, as you saw, that it is very easy to implement. So basic arithmetic, and it's computationally inexpensive. And as I told that earlier, that it can search very large spaces of candidate solution very quickly. And you saw that in the code demo how fast it was able to reach the global minima. And it can be easily parallelized for concurrent processing. So parallel computation can be done very easily, and it is insensitive to scaling of design variables. Basically, whatever values uh, the particle positions take, big or small, it's insensitive to that. Okay, and one of the disadvantages that, yeah, it can tend to result in fast and premature convergence. So this could be a case where all of the particle moved very fast and did not reach the global optima. So that can also happen if you play around too much with your acceleration coefficients. So that is one of the disadvantages of PSO. Main disadvantages, I would say. Also, one thing I would ask all of you to remember is that this is the basic version of PSO. There are actually many other versions of PSO which have been developed to cater to specific problems, and which can negate few of the disadvantages of the general PSO. So that needs to be looked into. So don't restrict yourself to only this basic PSO which I have displayed today. There are other forms of advanced PSO as well, which can perform even better, and if possible we might have to look at in some other session. And one of the looking going to the applications of PSO, yeah, it can be used for parameter optimization for deep learning models. So there are these papers which have been published wherein they've used PSO for parameter optimization of deep learning. For example, to find out what would be the ideal number of hidden layers, or the ideal number of neurons in the particular hidden layer. So it can be used or thought of as an alternative to grid search. And second is, yeah, as I told, it has been used to train feed forward neural networks. And yeah, uh, here in this particular paper, they have used to improve the training efficiency of reinforcement learning. So again, uh, as Vivek was suggesting, on reinforcement learning. So here they have used this optimization algorithm to improve the training efficiency of this particular in reinforcement learning. And another interesting is that uh, areas that use of PSO in image enhancement. So if you want to, let's say, improve the characteristics of that image, say pixels, or it can also be thought of an optimization problem, and you can use PSO for that. So these are the few of the applications of PSO, and you can actually go through these papers to understand in depth of how they have been how it has been used or deployed in various domains like deep learning or reinforcement learning or image processing. So, yeah, so these are the topics which we covered. So we looked into optimization and its disadvantages of gradient descent. Then we briefly understood PSO and its working with the help of sphere function minimization, and we understood the influence of user parameters in PSO like the acceleration coefficient C1 and C2. And then we also looked on the advantages, disadvantages, and applications of PSO. So that's about it from my end.
Okay, that's great. Audience, any questions? Actually, there are a couple of questions from before. Let me ask you. Could you please share the notebook with participants? So that is your call, Nikhil. If you want to share your Jupyter notebook with this audience. Uh,
Yeah, yeah, I can. It's a basic. I can share in the just a second.
yeah, you can send via chat the Google Drive link by chat, and that will get transmitted to all the current audience. And meanwhile, I'll ask you next question. Some of the packaged algorithms, do they internally use this for optimization?
Uh,
So I am assuming the question is around current MLDL algorithms. So they by default, they don't use this by default. So I think you'll have to adapt the current algorithms in MLDL to use this, right?
yeah, yes.
Let's say scikit-learn or TensorFlow, they don't use this by default. They have their own, the usual traditional algorithms. I think Nikhil has sent the link to his Google Drive to entire audience, so you can get that code. Uh, Next question is PSO comes under non-gradient based optimization method. So it's just a comment. So PSO, which category it comes under? So there's a comment saying that it comes under non-gradient based optimization technique. Okay,
Yeah, so
clear.
basically these heuristic problems are non-gradient based approaches. Yes.
So this need not do anything with AI and ML. This could be a standalone topic, right? So it can be applied to MLDL, but it can be a standalone topic.
Yeah, definitely. So that's the initial comment I made when I started. So optimization as such is a very generic topic and it can be applied anywhere, not necessarily machine learning.
It's complaining on access. This notebook you shared,
Hmm.
I think it's restricted, so you will have to make it shareable. I cannot access it. Yeah, you'll have to change to anybody. No, change to anyone with the link at the below. There's a blue tag. Yeah, correct. You can share that again. Audience, any other questions meanwhile? Yeah, now the IPYNB file is opening. It is opening fine, I believe. There is some package you mentioned, PySwarm, which has
Yeah.
ready-made APIs for this, right? Okay. Okay, audience, any other questions? Yeah, there is a question here. Okay, thank you for the great session. Thanks for that. Thanks to Nikhil for an excellent content and presentation. Audience, any other questions or comments? Okay, so we are not getting any other questions. So There's some positive feedback coming. Thank you for that, and thanks to Nikhil for all that. So thanks a lot, Nikhil. Very well done. Fantastic session, and look forward to more such kind of discussions from you. Okay.
Yeah.
So thank you,
Thanks
audience,
all.
for attending.
Yeah, thanks for joining.
Thank you all. So we'll see you later, and we'll hope to get more sessions from Nikhil in future. Thank you.